as I recall from readings from stuff from Terra, it's all sub 1 mil that you can get to with the A-SAP process. Is that correct?
Quite easily, actually, with a lot of the technology that's installed in the shops in North America today, we can get to sub 1 mil lines and spaces. The technology itself can go far much smaller, but it requires far more sophisticated equipment to do that.
Hello, everyone, and welcome to the Altium On Track podcast. I am your host, Zach Peterson, and I am sitting down today with Mike Vinson from Averatek. Mike Vinson and all of the folks at Averatek are highly knowledgeable in additive processes for PCB manufacturing, and that's exactly what we're going to be talking about today. I think it's going to be a very illuminating conversation, especially as we kind of continue the theme of designing with manufacturing, not just designing for manufacturing. Mike, thank you so much for joining us.
Thank you for having me, Zach. I look forward to talking about what we're doing at Averatek and how it fits in with the design community at large.
Yeah, absolutely. And maybe before you get started, or we jump right into the additive process discussion, maybe you can tell the audience a bit more about your background and how you got started in PCB manufacturing.
My background is in interconnect. It started at Texas Instruments a long time ago, back in 1984. And from there, we went to different types of die interconnect schemes. Then from there to surface mount, and from surface mount into PC boards. Averatek was started about 15 years ago to emphasize a new technology that was created at SRI International. And that technology is something that we've been using ever since. And we'll go into that a little bit more in a little bit.
So, Mike, I think those who pay attention to PCB manufacturing matters within the industry probably best know Averatek for its additive processing. And so maybe you could describe that a little bit for those in the audience who are not familiar with Averatek's process and then additive processes in general. Because I think when people think additive PCB manufacturing processes, they're probably thinking 3D printers.
Yes. So we're doing a lot of things in the additive world right now, along with semi-additive processes. I think one of our more popular processes is A-SAP, which is a semi-additive process that we use to make very fine features for high definition and high density interconnects on printed circuit boards. But we're also doing fully additive processes to add metallizations to 3D objects, to make patterns as well as circuits for things like patch antennas and different features on 3D printed objects. So I happen to have one here that I can share with you a little bit. I think you can see that. And that's a cone where we've patterned on the copper, and then that we have the ability to put that all around the cone in 3D. We can put patches on there. So we have a variety of ways to add the metallization, and not just copper. There's a lot of interest in other metals like platinum, gold, palladium, so that they're the more noble metals. And that's of a lot of interest to people who are trying to build these kind of radiation domes or cones with antennas on them.
Yeah, that's extremely interesting. And in this context, when you say additive or fully additive, you really mean the substrate as well as all of the conductors, not just...
Yeah, in this case, the 3D printing is done before we get the part, and that 3D printing is fully additive, where all of the material is just added on and nothing's really subtracted away. And then when we get it, we put a pattern on there that's all additive. So we're just adding the copper onto the surface, and we're not etching it away to make the pattern.
So it's basically a chemical deposition process on a 3D printed part. The 3D printed process really doesn't matter. It could be FDM, could be stereolithography, whatever it may be.
The 3D printing process, really, we're pretty agnostic to that. The materials, of course, we're somewhat dependent upon, but not totally. We haven't run into many 3D printed materials that we couldn't do well on.
You mean that you can't deposit on without strong adherence?
Correct.
I see. Okay, that's really interesting, and I think it's one of the things that it hopefully will drive more adoption of 3D printing within the actual electronics design process beyond just the enclosure. I mean, I know a lot of companies and clients, they'll keep a 3D printer in the office just so that they can 3D print their enclosures when they're doing prototypes and things like this, but no one ever talks about doing it at the board level, either because it's too expensive or because they want to go fully additive and they can't. Nothing's compatible.
Right. And it is difficult. You have to think through the issues, but we're working with some of the 3D printer companies to make sure that what they're thinking about in terms of how they print the device or construct it, and what we're doing afterwards, so that when we actually add the metallization on the surface, we can have a complete product that meets everybody's needs.
Yeah, and for as far as the markets that you're targeting, I mean, you had mentioned RF antennas. That could pretty much cover any application, but I would imagine unique form factor, wireless equipment, maybe mil-aero, some unique stuff like that.
Yeah, there's a lot of things that are going on, especially with the new 5G protocol for cellular towers and such that require very specific and very precise patterns put on surfaces. And we think that these techniques that we're using can be used to make higher gain antennas and lower power consumption electronics for these applications.
Yeah, I think within 5G, this gives you an opportunity to maybe hide smaller form factor repeater stations in plain sight almost. That's one of the things as the 5G frequencies get higher and higher. You need to have more of these micro stations essentially spread all over the place. And I think if you've never thought about it in this way in terms of like an additively manufactured product, you start to wonder, well, what does that look like? Do we have like these little mini cell towers on every block? And so
yeah,
the form factor is really, I think, significant there.
And we're just beginning to scratch the surface on what we're capable of there.
Yeah, that's really interesting. And then I wonder what has to happen in the CAD tools to be able to do this. For those in the audience who have some experience with MCAD tools, I know that it's possible to basically convert files into STL files and put them onto a 3D printer. This seems like a little bit of a different beast because you're not generating printing instructions. Right, you're generating. What are you generating from design files in order to actually use your process and then get that onto a 3D object?
So we're doing two things. We're generating a profile of the 3D object so that as we go through the process, we know where the surface is that we're depositing on. We deposit in very small areas actually, and process those in patterns. So we need that to be in focus when we do, and we need to know the contours that we're dealing with. After that, it's pretty much a bath process. So we're going to code everything that we touch. But there are some inputs of like step files to be able to program in that profile. And then there's also the pattern that we project onto that curved surface that we program into the machines. But after that, it's simply a matter of pushing the button.
Okay, yeah, entirely passive process, essentially just deposition.
It's pretty much just deposition, but it is very selective deposition.
Sure. Yeah, that makes sense. So you have to coat with a seed layer, essentially.
Yes, we coat with a seed layer, and then we cure that seed layer and leave behind a seed of palladium. And then that seed of palladium is used to then plate the electroless metals on top of it.
Got it. Okay. Fun. Sounds pretty standard, too. I think anyone that's dealt with electrochemical deposition processes could wrap their head around it, and it doesn't sound like it would be too much of a lift to incorporate this into other standard processing steps or possibly into a facility without much effort.
Yeah, it should be very straightforward, and we're talking with a couple of different customers who are looking to implement this right off the bat, and we find that they have basically all the tools that they need to do this up front outside of the Averatek chemistry. And a lot of those are implementing the Averatek chemistry for other projects as well. So they're pretty much good to go as soon as we get the process transferred to them.
Sure. So companies are licensing the chemistry from you. That's your IP. And then
they're licensing the technology. Yes,
Yeah,
they're licensing the technology from us, and they're buying the chemistry.
sure, makes sense, So, uh, are you focusing just in North America? Are you focusing worldwide? I mean, what's the geography here?
So we have some small inquiries worldwide. Primarily, our focus is North America right now. We're dealing with a lot of companies who need to keep their business in North America for security reasons or other reasons. And they're very interested in having this capability onshore. So we're working closely with them. It's also easier for us to do these first implementations onshore. And then after that, we'll look at what it would take to, or what's actually possible for us to do in the international market.
Sure, I can imagine with maybe export controlled products or possibly just products that are still in development, not ready for broad release, it might make sense to use this process at a prototype manufacturer to try and finish your development, perfect your form factor, make sure that you get a design that works best.
Yeah, for prototyping, things like 3D printing work very, very well. And the ability then to put these circuits on so easily also will be a real asset. So you can turn prototypes very quickly with this capability.
And then if you were, and we haven't mentioned this part yet, but if you deposit circuits on maybe not a curved surface, but maybe a 3D surface, and it has flat surfaces, can you actually assemble on it? Is it solderable?
Yes, yeah, we've done soldering tests where we have taken not necessarily 3D printed parts, but molded parts that are 3D objects, and put the circuitry on them, and then did soldering tests, the reflow test, pull tests on the soldered parts. Found very good results on those. Again, it will depend on your substrate, but the metal is copper in most cases, and that is always very solderable.
Yeah, because I could imagine having maybe like a square and then mounting all of your, or a cube, I should say, not a square, have a cube, and then mounting all your components on the sides. That'd be kind of interesting because, MIDs, or molded interconnect devices, the last time I had discussed these with anybody was probably 2018. And this was before companies like yourself were really coming out and pushing these types of processes, at least to my knowledge. And it was always viewed as something that was, really cool but too expensive, or, it looks nice but not really commercially viable. We're sticking with planar. And you guys seem to have really, kind of helped people change their perspective on what you can do with assembly, especially in 3D.
Yeah, so we're going for cool and not that expensive.
Yeah. Everybody likes that, right?
Yeah.
So you guys were recently at IPC Apex as well, and actually one of the authors on the Altium blog, Tara Dunn, she's our resident Flexpert. She has also been out on the road with you guys, talking quite a bit about A-SAP and Flex in general. But maybe, and we'll actually link to some of her stuff in the show notes, but maybe you can tell me a bit more about what's in your IPC paper.
So first, full disclosure, Tara is our VP of Marketing here at Averatek. And in the IPC paper, we talked a lot about what it would take for a designer to use a tool like the Altium tool to take a current design that maybe is 4 layers or 6 layers, and then convert that to a design that's 2 or 4 layers by using finer and finer features, fewer vias, and then through the fewer lamination cycles or the fewer layers, you can also get higher reliability. And the paper addressed those issues, looked at the performance that you would get from the new product as well as the old product, and then talked about how some of the modeling techniques that are being used to be able to do that, to enable a designer to take advantage of the feature sizes we can deliver with the A-SAP technology.
Yeah, because one thing that's kind of a double-edged sword of CAD tools is they allow you to do just about anything within whatever is defined as a limit in the software, but may not necessarily be manufacturable. And so you guys are really pushing the limit, it sounds like, of what you can do inside of a tool like Altium or another CAD program.
Yeah, well, actually, we're helping them exercise their limits, I think. It's more of an enabling technology, and it allows a lot of the things that designers have been envisioning for a long time to be realized. And also, since we're implementing it first in North America, a lot of these designers who are local here can now work with local shops to be able to take their design to reality.
Yeah, and I think it's fitting in nicely with the onshoring narrative that's going on, especially around electronics manufacturing, and trying to keep some of those advanced designs here in the U.S. Because I know that IP protection it's something that we've all kind of complained about for the last 10 years or so, and it's only now after a worldwide pandemic that we all start to really care about it when we can't get, the newest iPhone on time.
Yes. Something like that, yes.
Yeah, something like that. Yeah, exactly. I found that interesting because we were actually talking with the CEO of Elmatica on a previous episode of the podcast, and his entire discussion was about manufacturing capabilities in the U.S. and making sure we can keep some of that manufacturing for those mission critical components and products in the U.S. And I'm hoping that bringing these processes back into the U.S. and making them mainstream allows us to do that, but do it cost effectively, because at the end of the day, the economics dominate. So, I mean, with the economics in mind, what do the economics look like? Are the cost constraints too much of a challenge for everybody? Is this something that's going to be more accessible? Is this just going to take more time to really get there and be something that is cost competitive? Or is it going to just be one of those things where, the A-SAP process is great, but I can only afford to use it on something where, let's say, the DoD is throwing money at me and I absolutely must keep everything on shore due to export control restrictions?
So the A-SAP technology has shown itself to shine where there are shops that have installed capabilities, such as those shops in North America, that can install the A-SAP process for a very low cost, bring it up and running, and then be able to produce parts. And as I mentioned earlier, if the designer can redesign a 6-layer board that's being built in that shop to a 4-layer board, they're going to see a cost reduction in that component. So not only are we going to be performance competitive, we're also going to be cost competitive. And as things shrink and we have fewer components to deal with in the manufacturing, the reliability and yield will also increase.
Sure. So the cost is really being driven in two directions, right? The manufacturer, who has to actually implement the A-SAP technology, but then you're mentioning that it actually can save the designer money, or they can go to a more advanced product without increasing their cost.
Right. And a lot of trouble that we're seeing these days that the designers are facing is that they have a shrink in the BGA ball pad pitch. And those shrinking pads or shrinking ball pitches are creating a lot of grief to be able to interconnect to those pads. But with finer and finer traces, we find that we can get more and more signals through those shrunk pad spacings and then create a solution on fewer layers than you would be able to with the cruder technologies. Or you can look at it as being able to just shrink the BGA, use the more modern package that's accessible, and then create a solution out of that.
Yeah, that's interesting. And I know with BGA assembly, there can be many chances for defects, especially when you get to that smaller pitch size. So that's great that you guys have a process that can really help address that and hopefully increase reliability and yield. One thing that I was actually wondering, kind of as we're talking about this, there's one 3D printing company that I've worked with in the past, and their value proposition is their broad material set, and they actually kind of market themselves as having some of the most advanced low loss materials. And so, of course, that brings up the question of what plans are there to expand the material set? Can this work with some alternative material sets? And is that really scalable, or is it just the A-SAP specific chemistry?
No, it is scalable. We've been working with a lot of different substrate suppliers, for instance, in the printed circuit board area, working with companies who are producing substrates that have sometimes been thought of difficult to work with or difficult to adhere to. and we're finding very good results with a lot of their products. So we're creating a very large portfolio of substrate materials that we can work with. And from those, we think that we can derive a very broad area of applications that we can attack. Maybe not everything in terms of substrate materials, but probably almost everything in terms of applications, because we can find parallels there between the different dielectric constants and different CTEs of the materials that will work well.
Yeah, because I'm wondering if you have material from vendor A, material set chemistry from Averatek, and then a machine from a third party. And the third party could essentially implement a process that brings it all together and really lets the designer have some more flexibility on what material sets they're going to use to try and get the best results for their product. So like super low loss dielectric inks, plus then an additive process to deposit conductors. I mean, do you see that? Do you see that happening? Is that on your roadmap?
Oh, we're testing all the time. We see a lot of low loss materials that they're building products using our technology, the A-SAP technology, the LMI ink material that we sell, along with these new low loss substrate materials that they are getting quite high performance out of. So everything from making these cones, like I was showing you, which is a very advanced material set, low loss, up to a printed circuit board that's extremely thin and using very fine features on it. We're finding a broad acceptance and actually a lot of traction in the market right now.
So how does a designer take advantage of this? And what I mean by that is what manufacturers could they talk to start implementing this? And I'm not asking you to endorse anybody or anything like that, but how do they find out what they need to do to go and take advantage of these capabilities so that they can create more compact, smaller features, more advanced products?
Well, the first thing to do is contact Tara Dunn, who, as I mentioned, is our VP of Marketing, and she can put them in direct contact with the best licensee that we have. We have 3 licensees in commercial licensees in North America. We have several that are more captive in the Mill Aerospace area, but commercial ones, she can put them in touch with the best ones for their particular product, their particular need to match what their design criteria are to the capabilities of those licensees, and they can begin implementing almost immediately.
Okay. So they can then begin that discussion with the manufacturer and get started.
Yes.
So one thing that just came to mind, kind of as we're talking about all this, is those feature sizes that you're getting down to. As I recall from readings from stuff from Tara, it's all sub 1 mil that you can get to with the A-SAP process. Is that correct?
Quite easily, actually, with a lot of the technology that's installed in the shops in North America today, we can get to sub 1 mil lines and spaces. The technology itself can go far much smaller, but it requires far more sophisticated equipment to do that.
Sure, yeah. That's generally the case with smaller feature sizes. But what about clearances? I mean, how dense can you really get? Because it's one thing to put, a sub 1 mil trace, but how close together can I put a bank of sub 1 mil traces?
So we've done pitches down to, we've got some pictures of things that we've done in the 17 micron wide trace and the 11 micron wide trace, 17 micron space. So sub 30 micron pitch with very good high aspect ratios on those traces. There are a lot of details about where you can go with this, but the spaces can be made actually as narrow as because this is a semi-additive process, the photoresist needs to form the spaces. So if you can resolve that photoresist down to a small enough feature, you can make an extremely fine space in between, because in the semi-additive process, we remove the base material underneath, and the base material in the A-SAP process is so extremely thin that even though the traces are very close together, we can etch that out easily.
Okay, I see. That makes sense. So kind of like with a stereolithography process or maybe like a DLP process, it's really just whatever the smallest feature size you can project through your lithography process. That's what's going to get you the finer features.
Right. And most stereolithography processes today don't really focus on fine features. They're focusing on more of an area and making those areas smoother and more compatible, so that when we get to actually making the circuitry, that's when we have to implement the finer features. And those are also something that we usually do with the finest features we do with the semi-additive process, but other features we can do with the additive process that are quite precise.
Sure. Yeah, that makes perfect sense. And then one interesting thing that just came to mind, with what you just showed earlier in the printing on the cone, that's printing on the outside area of a surface. Essentially, if you wanted, you could do it on a cube, and so you're coming up to outside corners. What about inside corners on a surface, right? So like I have a surface, and then it curves up, and I want to print like this. Can you do that with the A-SAP process?
With the A-SAP process, we can get into some very, very fine areas. The LMI can penetrate into very small areas. We get down into the 10 or 15 nanometer particles or opening size with the catalyst. And so we can make some metallized in some very, very small areas. And we've done some inside corner plating and other things with the A-SAP. The challenge comes with 3D objects, being able to pattern them. Once we've got them patterned, then we can build the metallization up without any problem.
And one other question that came to mind also, can you do anything on transparent substrates? So can you do this on glass?
Well, we're working now with some transparent polyimides, for instance, and we've done some other transparent substrates. Glass is a little more problematic. It requires a lot more surface finishing, and that changes the refractive index of the surface sometime. So there are some considerations to be made with transparent substrates and how we change the effects of the transparency. If you put a lot of very fine features on something that looks clear, you can actually look through it, but it will also distort the optical properties of the material. So all of those things considered, yes, we can deposit on clear substrates. And yes, there are some applications that can take advantage of that.
Yeah, because I was just thinking, if you have the transparent substrate, you have a unique material set, then you could possibly also do transparent conductors on that substrate. And then you could have transparent RF circuits on a substrate. So now we're thinking like, your radar system for your car basically being built into the windshield.
Yeah, and the thing about our technology is we make very dense and very conductive metals on these surfaces, but they are metals. They have a very high optical density too. They're not like some of the other transparent conductors like ITO. So with these very dense things, if we put them onto the surface, you can actually see through them. They're optically somewhat transparent, but they also tend to distort the image some. And so in a lot of applications, it's like the heater elements on your rear window. You can actually see those if you look close enough, but at a distance, they seem to disappear. And those are the kinds of things we can do with this technology.
Yeah, so you would want to do it in a way that doesn't prevent or create a distraction for somebody, like for the driver.
Right, but if you wanted to put, say, for instance, a very thin, fine feature in a coil all the way around a window or an opening, that would be a very high gain antenna for certain frequencies. Yes, that's doable.
Okay. Yeah, that's interesting. That's where you really start to take the printing of electronics, I think, to a new level that most people don't consider, is when you start doing things transparent. So that's very cool. I bring it up just because in my past life doing zinc oxide, we always tried to get to as transparent as possible deposition on glasses. So you guys are totally beating us in what we did.
Well, this technology gives you a much more conductive line for the same width, but it also gives you that very high optical density in that very small area.
Yeah, absolutely. So we're getting up there on time, but I definitely want to make sure to ask you this. What is the future of the A-SAP process or your additive processes, or even just the additive manufacturing realm in general? What do you see coming down the pipeline in the next few years?
So right now we're working on some technologies that will allow us to embed die in printed circuit boards or some very small modules, perhaps. and that embedding can be done with extremely fine features and all of the routing issues that we were talking about that get solved as the feature size goes down. We can get even smaller features on the die and then still route around those with this new technology. And it's an additive technology. And we're working on that with a number of companies right now to develop it out. That's what's one of the big things that's coming down the pike with this technology. The other one is this additive technology that you've been looking at. And we're looking at different ways to incorporate that into some high performance products, as well as things that have high reliability requirements like automotive.
And then the other area I think that often gets overlooked by, a little bit by the semiconductor side, but definitely by the PCB folks, is interposers. Do you guys have plans to apply this to interposers?
Yes, and we also have a technique we look at and call like an in situ interposer, where you can take our technologies and mix them and match them, so that if one has an extremely fine feature size, you can use that in one layer, and then you can put another with a more coarse feature size on another layer, and you can go all the way up to the current technology for, say, like a power and ground layer, and make it with that technology. So it's the ability to mix and match these different technologies to give you the kind of distribution you need within your solution set. And those interposers can be built either as small interposers that are freestanding, or they can be incorporated into the design of a larger printed circuit board.
Yeah, that's so interesting. I mean, this is excellent stuff. Thank you so much for being with us today, Mike. I'm definitely going to put a link to the recent IPC Apex paper into the show notes. Also, you had mentioned contacting Tara Dunn. I think what we'll do is we'll put a link to her LinkedIn profile in the show notes, if you're okay with that.
That'll be great, yeah.
Yeah, absolutely. And I would encourage anyone who is listening and wants to learn more about this process. We've got some links on the blog that we will include in the show notes. And then also, if you're interested in applying this for your own circuit boards, to please reach out to Tara Dunn over at Averatek. Thank you again, Mike. We've been talking with Mike Vinson from Averatek, and I think this has been a really interesting discussion on an area that I think is very cool, and I hope more people are going to become aware of in the coming years. Thank you again.
Thank you, Zach. Great talking to you today.
Thank you. And everybody out there listening, please go ahead and hit the subscribe button on YouTube, and you're going to see a lot more interesting discussions with technology leaders talking with us on the Altium podcast. Everybody out there, don't stop learning and stay on track.